All right, bring it back. So as several of you noticed, there was no quiz last weekend. Partly because I hadn't gotten your elements quiz back to you yet, and I don't like to give you another quiz while you have one outstanding already. And partly because I didn't see you on Friday, so I forgot about it. So you didn't miss anything. There was no quiz last weekend. So I think we're okay there, which means we only have a few quiz questions to address at the beginning of class. So why are there only 2 elements on the periodic table that are liquids? Anybody have a guess? What is, yeah, somebody said temperature. What about temperature? It's either too hot or too cold for most of the elements on the periodic table to be in their liquid phase. But if we pull up P table, it actually lets us look at that and change the phase or change the temperature. Let's see. Properties, there's a way to sort by. Oh no, there it was. It's right here. So if you look at this up at the top, if we play around with the temperature here, we can actually get more of them to start showing up as liquids or gases as we increase the temperature. So that only 2 of them is liquid at room temp at 25 Celsius. But that's just because that's room temperature for us. And in fact, out of those, I think if we go to 0 Celsius, at least one of those will change too. Nope, bromine and mercury are still liquid at room temp at 0 Celsius. But there it is. It was right below. So when you get to -40 Celsius, then everything's a solid. So it just has to do with the temperatures that we're used to. What about chlorine? Oh, it just switched from being gas to being a liquid as I dropped the temperature, right? So all those gases also have boiling points. So all those gases will start to become liquid the colder you get. Anybody know what temperature liquid nitrogen is? -2, close. -200 about Celsius. It's about 78 Kelvin. Is where liquid nitrogen boils. Oxygen's right around the same temperature. You can have liquid oxygen. You can have anything that's a gas at room temperature. If you cool it down enough, you can even have liquid hydrogen. You just have to get down to around 2 Kelvin. It would be really cold. You give yourself frostbite on your esophagus. It would boil really, really quickly too. So you would probably also give yourself a lot of burps. Because when it's liquid and then it turns to a gas, when it boils, then you have a whole bunch of gas in your stomach that has to go somewhere. So it would not be very pleasant, put it that way. You probably could blow up your stomach. Your stomach has a lot of give to it, but depending on just how much you drank, you could actually rupture your stomach potentially. Somebody asked about other universes, and since that's actually a fairly common question when we talk about quantum, because people talk about multiverse theory and things like that. Are there other universes we don't know about? I mean, the math kind of points to you could make that argument from a math standpoint. Basically, remember our questions about flipping a coin. When it's in the air, is it heads or tails? It's both simultaneously, right? But then once we measure it and we actually see it as heads or tails, one of the interpretations of quantum mechanics is called the multiverse theory, in that basically you cause the divergence and you cause 2 new universes. One where the coin was heads up and the other one where the coin was heads down. and so in that case, there'd be an infinite number of universes. But the thing is, it's not really science because we can't test that. There's no way we have of verifying that. It's just that the math behaves kind of like that, but the math also behaves like the cat's alive and the cat's dead simultaneously, right? So it's not really, we don't really have a good answer to that one, other than to say it's not currently science because we don't have a way of testing it. If you're interested in a decent sci-fi book about that idea, everybody know who Michael Crichton is? Known mostly for Jurassic Park, but has written a lot of the decent scientific sci-fi. He had a book called Timeline. It was kind of time travel on the surface, but it actually involved the many worlds interpretation of quantum mechanics as part of the premise behind it. Granted, it's been probably 20 years since I read that book, but I remember it being pretty good. So if you're interested in that, that sort of thing, then check it out. I like this next question because it doesn't make any sense, which seems like a weird thing to say about this question, but it brings up an interesting way of thinking about the Big Bang. Until the Big Bang, there was no time. So I guess I should say until after the Big Bang, there was no time. So what happened for the Big Bang, or what caused the Big Bang, is a little bit like asking what's south of the South Pole. Think about a globe. Where's the South Pole? It's the southernmost point on the globe, right? Where all of the longitude lines all come together. So what's south of the South Pole? North. If you keep going south, eventually you start heading north, right? So it's really a question that doesn't make a whole lot of sense, because you could say, well, it's south of the South Pole is not on the Earth anymore. Or you could say south of the South Pole is actually north. But it's a question that if you don't have time, how can something have caused anything? Right? You can't have cause and effect if there's no time. So it's not really a question. The other way it gets phrased is what was before the Big Bang. And that's the same thing. There was no before the Big Bang. So, because there was no time, which is just a weird thing to think about. And on a more practical note, if you want to think about what those big questions like what caused the Big Bang, what you want to look into is called cosmology. Cosmology, not to be confused with cosmetology. Cosmology is a study of the origin of the universe. It involves a lot of theoretical physics. That's actually what Stephen Hawking's field more accurately was. It wasn't just physics or astronomy, it was cosmology. And so you can read up on that. It's a pretty interesting field, but it does involve a decent amount of theoretical physics and philosophy, and really weird mind-bending ideas. So again, if that seems like it's right up your alley, check it out. And actually, a good place to start is actually Stephen Hawking's book called Brief Answers to the Big Questions. Which is, of course, a reference to his first popular book. Anybody know what book he was best known for writing? He wrote it in the 80s. So it's been a minute. Called Brief History of the Universe. That's also a decent place to start, but this is a more updated version that was published posthumously. He wrote it in the last couple of years, right before he died. Has some really, really good thought-provoking questions, and it's worth a look if you're interested in cosmology. Lastly, on a more practical note, is there a shortcut for subscripts and superscripts? Universally, no. There are keyboard shortcuts in Microsoft Office. It's a subscript is Control equals, and a superscript is Control Shift equals. And I believe it's Control period and Control comma in Google Docs. Other places, if you're like writing in text box on Canvas or on Reddit, its subscript is a underscore. So you could write MG_2 and give you MG2 if you're using what's called markdown language, which is what shows up in a lot of the online text editors. So, and then the opposite, if you wanted to type in MG2+, it would be MG parentheses 2+. Caret means raised to the, right? So in on a calculator. So when you're doing a text editor, you can use that as well. My recommendation is whatever text editor you wind up using the most, look up some of the more common keyboard shortcuts. Some of them are universal, like Control B always means bold, Control I always means italics. Superscripts and subscripts are a little bit more case by case. All right. How did the light lab go last week? Calculations aren't too bad. Not as much fun to just watch me light stuff on fire, but you can understand why in a classroom of 30 people, we don't let you all light everything on fire, because we'd be lighting everything on fire. If you have any questions on that lab, it'll be due this coming Thursday, so you still have time to finish it up. But our new assignment for this week is not a particularly exciting assignment, but it's the best way to get your practice, I guess, for nomenclature. When we said the polyatomic ions quiz, did I give you 2 weeks from Thursday? Okay, so it's not this Thursday, it's next Thursday. It's the polyatomic ions quiz, which is good because that also means you can be working on it while you work on this week's assignment / lab, which is just pure nomenclature practice. So covalent compounds, ionic compounds, and a new class that we're going to introduce today called acids. It's basically because nomenclature is kind of, I don't want to say boring, but boring for lack of a better word. I don't have a better way to practice it other than just sheer brute force. So your assignment this week is a big long PDF of nomenclature practice. It'll have some polyatomics. It'll have practice with Roman numerals. It'll have practice with covalent compounds. And it's just literally 14 pages of nomenclature practice. 14. 7 double-sided. With a couple, I think the last page has a couple of practice calculation questions that are a little bit more interesting. So when you feel like you can't stand doing another page of nomenclature, you can go work on one of the practice problems, the math problems at the end. So sorry, not sorry. It seems to work. This assignment is nobody's favorite, least of all mine, but the key will also be made available, so you'll have plenty of time and the ability to check that. And before I can just turn you loose on that, we have to add our last class of molecules. So for starters, we had covalent compounds, also known as molecular compounds, and we had ionic compounds. Let me skip forward for a second. So how do we tell the difference between something that has ionic or covalent bonds? Metal and a non-metal is one of your go-tos. If it's a metal and a non-metal, it's ionic. Can you have an ionic bond between things that are all non-metals? What about if we had a polyatomic ion that has a positive charge and a polyatomic ion that has a negative charge? So this is the one exception. Most of the time, all you really need to look for ionic compounds is a metal and a non-metal. But we have one common polyatomic ion that has a positive charge, which means if you see NH4+, better known as what? Ammonium. You see ammonium, and then a nonmetal, that's still an ionic compound. And I'm going to be a little bit picky on this one. This is ammonium, not ammonia, because ammonia is NH3 and it's neutral. So ammonia versus ammonium, you just have to be careful with that. Ammonium sounds like it's an element, right? Most of our metals end in -ium. So that's one of the ways you can remember which one's which. Other than that, though, if you don't, was there any other polyatomic on your list? Thank you. That had a positive charge? I'm asking a question I already know the answer to, right? There's one, hydronium. Hydronium doesn't really show up in ionic compounds, though. It's mostly there because we start talking about acids in more depth. It winds up being really important. But in theory, you could have ammonium chloride. It'd be H3O Cl. That technically could exist as an ionic compound. Not really that common. Ammonium chloride is really common. Ammonium nitrate is even more common. Does anybody know what ammonium nitrate is found in? Mirrors? It's a good guess. Silver nitrate gets used in making mirrors. And so you could actually get ammonium nitrate as a side product when you make mirrors that way. Ammonium nitrate is most commonly found in fertilizers, particularly relatively explosive fertilizers. Has anybody heard of the Oklahoma City bombing back in the early 90s? I want to say 92. I always mix it. It's the one that's not the Unabomber. Timothy McVeigh was the terrorist who basically just built a pickup truck full of ammonium nitrate fertilizer and parked it in a parking lot garage in a federal building in Oklahoma City and blew it up and brought down the whole building. So winds up having, and it's actually even more important historically, because the whole process of making ammonium nitrate actually is what caused World War I to be as bad as it was. Because up until a chemist named Fritz Haber found a way to produce ammonium nitrate in a lab, the way that you got ammonium nitrate, which is a key component both in explosives and in gunpowder, was by mining it. And most of the ammonium nitrate mines in the world in the early 1900s were found in South America. I want to say Chile, but I'm not sure entirely. South America for sure, though. And so what happened at the outbreak of World War I is very quickly the Western powers kind of consolidated and blockaded the Eastern powers so that they couldn't get shipments in. And so they thought they're going to run out of gunpowder. The war would be over pretty quickly. Until Fritz Haber found a way to make ammonium nitrate in the lab, which all of a sudden meant that the war could go on for a lot longer. If it hadn't been for that process being discovered at that time, then World War I would have been very, very different, probably a lot shorter. Plus the Haber process it's called the Haber process now. Basically, he found a way to take a nitrogen gas and hydrogen gas to make ammonia, which then you could convert into ammonium nitrate relatively easily. But that process was what wound up being really important, and it winds up, we use it all the time as an example in chemistry as well. It has a couple of other really interesting properties that make it a really good kind of model for studying some of these processes. So looking at the examples up here, do any of them have ionic bonds? No ammonium, so we don't need to worry about that. Which means we just have to look for what? Non-metal to a metal. PTO2. And other than that, they're all covalent or what are called molecular compounds. All right, so what's our rule for naming ionic compounds? That was a big chunk that just fell. What's our rule for naming ionic compounds? How do we name them? We switch the cation, the second element that's written, we switch the ending up to "ide." Other than that, we just say the name of both ions, right? So PtO2 is going to be platinum oxide. Do we need to specify which platinum ion it is? Does platinum have more than one charge? It's in the D block, and it's not one of those 6 that are all grouped together, right? So we need to specify what the charge is on the platinum. There's 2 of them. What's the charge on each oxygen? 2 minus, right? So the platinum has to add up to a total of +4, right? Because we don't need it to just be the same as the oxide. We need 1 platinum to have the same charge as 2 oxides. So the platinum's got to be +4. So 2 oxides and 1 platinum 4 ion. And again, if you don't remember how to write that, writing platinum 4 like that's totally acceptable as well. All right, so A is kind of tricky, but B and D, we can name both of those as well with our covalent compounds nomenclature. What's our rule for covalent compounds? Yeah, we use those numeric prefixes, the Greek prefixes, just say how many we have. Because there's a lot of different ratios of carbon to chlorine that you could write that still give us a valid compound. So we just specify how many we have. So CCl4, if we're putting prefixes on everything, we'd say monocarbon tetrachloride. Remember, we don't usually say mono for the first one. So it would just be carbon tetrachloride, which is a real fairly common compound. We use it all the time as a solvent in organic chemistry. And then how about D? Sulfur trioxide. Depending is another note about spelling of the elements. And one of the reasons that there's a lot of reasons why I'm not too picky about the spelling. But one of those reasons is that your spelling of different elements actually changes depending on where you are. In the UK, they actually spell some elements differently. Aluminium instead of aluminum. They spell sulfur with a PH instead of an F. And I think the second PH in phosphorus sometimes is actually with an F.
Cesium too, right?
And cesium, they switch the A and the E, and or they add an A. So we spell it cesium like this. They spell it CAESIUM. Right, so don't get too hung up on that. Depending on what periodic table you're using, this sulfur pH was the most common one. In fact, actually, if you're in a literature class, if you ever, I want to say, you read Cormac McCarthy in high school? If you don't read Cormac McCarthy in high school, you should. All the Pretty Horses and Blood Meridian are fantastic, if rather nihilistic novels. I want to say that Cormac McCarthy, who is an American, uses sulfurous with a pH. I think sulfur, something smelling sulfurous, gets spelled like this all the time, which just looks a little bit odd, but that's the literature way of spelling it, and that's the chemistry way of spelling it. So again, I'm not going to be picky. Take your pick. There were a couple other notes I had about the quiz while we're on talking about this. I'm surprised at how many of you got thrown by radon, but I suppose that's not really fair considering that I asked the question backwards. So everybody got the point for radon, whether you marked it as radon or marked it as rhomgenium, or rubidium, whatever you wrote it as. There was one other common misspelling though. What is this? It'll come to me. Or it won't. All right. So I will. This slide is your cheat sheet for all of your nomenclature. All your nomenclature rules on one slide here. Ionic and molecular, we've already gone through those, and they're both pretty straightforward. Acids are also relatively straightforward if you know your polyatomic ion. The acids use things a little bit differently. And the way we define an acid in this class, at least, is it's basically an ionic compound where your cation is hydrogen. If you see an ionic compound, or you recognize, for instance, I wrote HNO3. NO3 with a minus charge is what? Nitrate. So anytime you can recognize a polyatomic ion that then just has a cation, where the cation is a hydrogen, is an acid. Technically, it's only an acid when it's dissolved in water, which we write like this. But nobody's going to really think twice if you call this an acid. Right? And the way we name these, instead of just saying hydrogen nitrate, for whatever reason, they decided to keep a totally different naming system for acids. Instead of saying hydrogen nitrate, you go off of what the suffix is on your polyatomic ion or your anion. So if it ends in 8, so if it ends in 8 here, you drop the 8 and you just put IC. IC. So hydrogen nitrate becomes nitric acid. So 8 turns to IC, and then you just say the word acid. If it ends in ite, you drop the ite and you write OUS. Acid. So nitrite becomes nitrous acid. And then what's the other suffix? Well, the other suffix that we can have on a negative ion is "ide," right? Our simplest ones, like chlorine becomes chloride. If it turns into I, or if your anion ends in "ide," you throw hydro onto the front and then put the "ic" on the back. Right, and so there's various, ways you can remember this. The one that I've heard before is I ate something icky. Sprite is delicious. My ride has hydraulics. I have a not so clever way, but maybe just as useful way. It's really dumb. But I use it as an example all the time. Find whatever works for you. It doesn't matter if it's dumb. I had a friend in high school whose name was Titus. And so I just remember that us sounds like my friend Titus's name. It's silly. But I still use that to remember it. I still think of my friend from high school named Titus every time I teach this class because of this connection. It just sounds like his name. That's all. That was the only connection. And now you too, every time you're naming acids, you will think of my friend Titus. Because now you won't be able to forget that. Right, and then I always just remembered that the simplest formulas had the most complicated name. Because what's an example of something that ends in "ide"? Chloride. So chloride as an ionic compound with H is the positive ion would just be HCl. The simplest formula, but the most complicated name. Because what name do we get for HCl? Hydrochloric acid. Right. Again, technically, it's only hydrochloric acid when it's aqueous, when it's dissolved in water. But that's kind of splitting hairs. If you have HCl as a gas, you actually name it as an ionic compound. You just be hydrogen chloride. But when it's dissolved in water, you name it as an acid. I'm not going to split hairs that much. So if you named this hydrochloric acid, I'm not going to mark you down. I'm not trying to catch you tripping up on anything. That's close enough to the same thing. All right, so if we're going to name these acids properly, we need to know our suffixes and formulas and charges, which is why we have to memorize our polyatomic ions. You can't get the right name for these acids if you don't have the right suffix on the end of your anions. Do one more example real quick. The key here too is that you have to have enough hydrogens to make it totally neutral. Right? So for something like chloride only had a -1 charge, right? So you only need one H plus to balance that out. What about one of these? Well, H2O would work. But how about sulfate? Sulfate is SO4 2-. So we have to add 2 hydrogen ions to make it balance out. So now this is balanced. The charge is balanced. Charge adds up to 0. Now we name it as an acid. What would we would name this? What would we name this? So 8 means ick. Technically sulfic acid, but it's a little bit of an irregular the way you conjugate it. So sulfuric acid. There's a couple of them that are just having that extra syllable gets put back in. Phosphate's the other one. It's not phosphoric acid, it's phosphoric acid. But for the most part, you drop the 8, right? Ick. So sulfuric acid. We did this with carbonate. Carbonate's another good example. What's the formula and charge for carbonate? C. All of the 8s have oxygens in them, right? So we know CO, how many oxygens for carbonate? 3. Good, Glenn. What's the charge? -2. Carbon's got an even number of electrons, right? Which means your charge is going to be an even number as well. Because all of our polyatomics add up to an even number of electrons. So if carbon has an even number and oxygen has an even number, your charge has to be an even number. So what would the formula be if we made this into an acid? H2CO3. And we would name it carbonic acid. Good. It sounds weird to say that is one that doesn't roll off the tongue. You're not used to hearing that name. You've probably heard sulfuric before. You probably heard the word phosphoric before. You probably have not heard carbonic acid before. But Everybody has experience with carbonic acid. Carbonic acid is what you get when you dissolve CO2 as a gas into water. Where does that happen? Soda or bubbly water, right? Bubbly water has a bunch of CO2 dissolved into it, which makes carbonic acid. The CO2 reacts with the water to make carbonic acid, which is why bubbly water has a little bit of a bite to it. Why it tastes acidic, because it is. You literally made carbonic acid by dissolving, well, not you personally, unless you carbonated it yourself. But you made carbonic acid by dissolving CO2 in there. This is also why almost nobody, unless you have like the sweetest palate that I've ever heard of, nobody likes the taste of flat soda, right? What's wrong with flat soda? It's too sweet, right? Because you're missing all of your carbonic acid now. So you don't have that tart, sour bite to it to balance out the sweetness as much. All right. Questions on nomenclature or carbonic acid? All right. Then let's talk a little bit more about covalent compounds. Because when we were talking the other day about covalent compounds, we made the point that it's not always the lowest whole number ratio. Right? With ionic compounds, the formula is always the lowest whole number ratio, because with ionic compounds, we're just looking for whatever makes the charges balance out. But with covalent compounds, particularly, they don't actually split apart. So we're not actually looking for the lowest whole number ratio. The lowest whole number ratio is what's called the empirical formula. And that's called the empirical formula because one of the earliest ways we had of determining these things was literally we could figure out what the percentage by mass was. So if you knew that the percentage by mass for a particular compound, then you could work out what the lowest whole number ratio of these atoms was. But it didn't necessarily tell you what the molecules looked like. So this is another fairly common compound. The formula for this compound would be H2O2. But that's not the empirical formula. The empirical formula, what's the lowest whole number ratio? It would just be HO, right? 1:1. But that doesn't tell you the whole story, because you can also have a different compound. You write it like this. This is HO as well, except this dot means it's got an unpaired electron. It's got an odd number of electrons, which is really, really unstable. Does anybody know what term gets used when you have an odd number of electrons? You have unpaired electrons. It actually got used a whole bunch in nutrition and health marketing for a few years. This is called a free radical. A radical in organic chemistry just means it has an unpaired electron. And an unpaired electron is really, really unstable because it's basically going to go out and find another electron so that it can become paired up. When it does that, it breaks up another pair of electrons. And so you get this chain reaction where once you get free radicals involved, they just start breaking stuff down. Which, incidentally, is what happened with the hole in the ozone layer. If you have ever read about that or heard about that, it's somewhat healing itself now, but basically there were these compounds called CFCs that chemists and chemical engineers thought that they were really, really good material to use as refrigerants, propellants, and things like that. And they were really good for that. They're inactive, inert at sea level, really, really easy, not a whole lot of health concerns with it. The problem is when they get to the upper atmosphere, they could get hit by the high energy UV light from the sun that's in the upper atmosphere, and they would split up into radicals. And the radicals, the most molecules that the radicals were finding to react with were ozone molecules at that particular altitude. And so they wound up breaking down all the ozone that was naturally present in the upper atmosphere that helped a lot with absorbing some of those high energy UV light. So anyway, a brief aside, all that to say, these are not the same thing. If you shine UV light on this, you get this, but they don't behave the same. So we need to be able to describe them differently. And so that's why we use the molecular formula, which is the total number of atoms in the molecule, not the lowest whole number ratio. Right? Another good example is molecule here. What would the molecular formula be? How many of each atom do we have? H6C2O2. That's not the empirical formula. What would the empirical formula be? Just divide everything by 2, right? So H3CO. This is another everyday molecule. This is ethylene glycol, which is found in is the primary component of antifreeze. So a lot of things that have where we need to be really specific in terms of the formulas, we need to make sure we're not just giving the empirical formula. We want the molecular formula. So then one of the key things we have to keep in mind then is that how do we show the structure? One of the ways you can show the structure is just by writing the molecular formula. But what if I wanted to show the molecular structure, not just H6C2O2, if I actually want to draw it like this, how do I know how to draw it like this? Part of it's memorization for me. Part it also follows a couple of key rules. Right, and I guess just to define some terms, when we're showing the actual structure, we call that either the structural formula. Instead of just writing H2O2, if we actually show what atoms are attached to what, that's called the structural formula. And there's a couple different ways of looking at the structural formula. You can use what are called molecular models to start showing a little bit of three-dimensional shape. So this is a really common biological molecule. Anybody know what that is? Six carbons, 6 oxygens, 12 hydrogens. Sugar, it's glucose. These are all 3 glucose. Right, so depending on what we're trying to show, we can actually write them differently. If I don't actually, if I don't need to show the entire structure, that's actually a lot more writing than just writing out C6H12O6. If you know that that's glucose, you don't necessarily need to show the structure of it unless we're talking about some particular aspect. Because this also gets confusing because there's other molecules that are C6H12O6. In fact, there's other sugars that are C6H12O6, like fructose. Fructose and glucose have the exact same formula. In fact, the only difference is that that double bond between carbon and oxygen there is shifted down 1 carbon. You get a carbon double bonded to an oxygen on the second carbon instead of the first carbon. It's the only difference between glucose and fructose. Fructose tastes sweeter though. All right. So how do we know how to draw these things? It's pretty clear that just writing the molecular formula is not always going to be enough, especially if we go into studying organic chemistry or biochemistry, where the actual three-dimensional shape winds up being really important. the three-dimensional shape of fructose versus glucose is why fructose tastes sweeter. It actually hits different taste receptors on your tongue because of its shape, because of where that carbon-oxygen double bond is. So being able to actually write these out winds up being really important. So how do we draw these? We're going to start with things that are simpler than glucose. And we're going to do what's called a Lewis dot structure. Right? A Lewis dot structure I kind of hinted at the other day. But a Lewis dot structure is basically how do we arrange these electrons in a way that everything has a full valence. Right? So there's a couple of key criteria. These are both two different ways of drawing the same thing. So how do we decide what's attached to what? There's a couple of things we need to keep in mind. Right? When we're trying to draw these structures out, the three criteria we always need to pay attention to is in order of importance. Most important, we have to use the right number of electrons. We can't just be creating electrons out of nothing. Frowned upon. In addition to having the right number of electrons, why do we make these covalent bonds in the first place? What is it about nonmetals that makes them form covalent bonds? They're sharing to do what? To fill the valence shells. So after we make sure we have the right number of electrons, the next most important criteria is we have to make sure that we fill all valences. And then last but not least is something we're going to come back to in a little bit. We also want to make sure we have the formal charge has to be closest to zero. That doesn't make a whole lot of sense yet. So we're going to ignore that one for a bit, but I just want to put it up there because this is what the three criteria we will always come back to with these Lewis dot structures. Get the right number of electrons, and then you arrange the electrons so that everything has a full valence. This last one comes into play when there's more than one way we can accomplish the first two. All right, so here's our steps. We're drawing a Lewis dot structure. First step, you place your atoms on the page somewhere, on the whiteboard. And usually you place the central atom. And the way we decide what's the central atom, there's a couple of ways of thinking about it. But basically, whatever is going to make the most bonds or has the most vacant spots is going to go in the middle. So if we had, the text box got too small. It's supposed to be H2O. We have H2O. What atom is going to go in the middle of H2O? Oxygen. Oxygen has two empty spots, right? Then you just put your hydrogens on either side. You just take all the other atoms, you just spread them around that central atom. Then we count up our total number of valence electrons. What do we have to work with? So in this case, how many valence electrons do we have? We've got H2O. Each hydrogen has how many? One electron for each hydrogen, and we have two hydrogens. We have one oxygen, and how many valence electrons does an oxygen have? 6. Count over on the periodic table, right? Count over columns, skipping the D block. So we have a total number of 8 valence electrons. So here's where we're starting. All we're going to do is start arranging these electrons so that everything can have a full valence. Usually the best way to do that It's whatever's surrounding that middle atom. Start by drawing a line. Connect these. You have to have a bond between these, or else it wouldn't be molecular compound. They wouldn't be part of the formula if they weren't connected, right? So how many electrons did I use to do that? 4. Remember, each of these bonds counts as 2 electrons, right? Because you have to have 1 electron from each atom for it to be a covalent, right? For those orbitals to overlap. So we use 4 electrons. So we have 4 electrons left. Once we have everything attached, all we do is we say, okay, 4 electrons left. Look at your outermost atoms. See how many more electrons they still need. How many electrons total does hydrogen need to have a full valence? Total. It needs to gain 1 electron based on where it is on the periodic table, right? So it only needs a total of 2 electrons to have a full valence. So these hydrogens are stable. These hydrogens, the way it's drawn, these hydrogens are good to go. They've got a full valence. We have 4 electrons left, though. We have to put them somewhere. Does the oxygen have a full valence yet? It's got 4 electrons. It needs to get to a total of 8. So we put those last 4 electrons around the oxygen. You don't have to draw this little loop. I use it because when if you just make small dots, it's easy to miss those electrons. So it's a way to remind yourself that those electrons are there and they take up space. So now how many electrons are left? Done. So criteria 1, right number of electrons, we're good to go. Criteria 2, does everything have a full valence? The hydrogens are good. The oxygen's got 8, right? Oxygen's in the second row of the periodic table. Oxygen needs to get to 8. For almost always, you need to get to at least 8 electrons for it to be a full valence. The only 2 elements where you only need to get to 2 are what? Helium and hydrogen. And helium doesn't form any bonds. It really is just hydrogen. Everything else needs to get to 8 electrons and can go, some elements can go past 8 electrons. That'll come back with the formal charge discussion in a minute. All right, so put your oxygen in the middle, hydrogens. You can draw your bonds as a pair of dots if you like. While you're first getting used to this, that can be an easier way to remind yourself that there's 2 electrons per bond. Is there anything different about the way that I drew it versus the way that it is up there? 90 degrees versus 180 degrees, right? Or does it? Turns out it doesn't really matter. So this is getting into what we're going to talk about here in a second. Basically, every pair of electrons around the central atom is going to take up space, because what do electrons do to other electrons? They bond. In some cases, what else do they do though? What's the charge on the electron? Negative. And what do negatives do to other negatives? They repel each other, right? Opposites attract. So if we actually have these 4 clouds of electrons around this oxygen, they're naturally going to arrange themselves so that they're as far apart as possible. They still have to be around that middle oxygen though, so you can't just physically separate them out, because they still have to be attached to that middle oxygen. So what happens is you actually wind up with them always arranging themselves to be as far apart as possible, which would be, if we're not going to rank how far apart they are in terms of a distance, we rank how far apart they are in terms of an angle. So what's the angle between each of the electron groups? As it's drawn on a flat surface, it'd be 90 degrees between each one, right? Except that we're not on a flat surface if we're talking about these molecules, are we? We have 3 dimensions to work with. So they actually spontaneously rearrange themselves to be in 3 dimensions. Can't quite get to 180, but we can make what's called a tetrahedron. That looks, anybody play Dungeons and Dragons or similar games with polyhedral dice? A tetrahedron is in the gaming community is known as a D4, 4-sided die. Or you can think of it as a 3-sided pyramid. Basically, these electrons all arrange themselves to be as far apart as possible, which results in them being about 109 degrees from each other. So a little bit further apart than our 90 degrees here. And it turns out once you have this shape, I guess I should explain that how I drew this. This wedge is supposed to indicate a hydrogen coming out of the board towards us. And this dotted wedge here is supposed to indicate a hydrogen going into the board away from us. So basically the hydrogens and the oxygens make this sort of V shape that's about 109 degrees between the 2 hydrogens. And it turns out it doesn't actually matter which way you draw the hydrogens on a flat surface, because you can take this molecule and twist it around and draw it however you want. It's always going to arrange itself, and you're always going to have a hydrogen that's adjacent to the other hydrogen and one lone pair and the other lone pair. And so it's always going to have that same shape. So because we're drawing something in 2 dimensions, it's actually 3-dimensional. It looks like we could have 2 different ways to do it, but it turns out this and that are equivalent, right?
What's the most complicated shape in the order system?
If we're still talking about with just a single central molecule or single central atom, then sulfur hexafluoride. Sulfur is one of those ones that can actually break the octet rule. You can actually have up to 12 valence electrons for sulfur. And so this one actually looks like, you can imagine these 4 fluorines as being square, going into the board and out of the board. They're basically all 90 degrees from each other, but flat into the board and out of the board. And then there's one that sticks up from that, 90 degrees to the plane of these 4. And then there's one that sticks down from that. So again, going back to the polyhedral dice, this is a D8. 8-sided die, you get an octahedron, which seems weird because it's actually only hexafluoride, but you get 8 sides when you look at the shape that's involved. And we'll talk more about these shapes in more detail here in a minute. But there's really no limit. We actually wind up using the wedges and the dots all the time in organic chemistry, because as we get larger and larger molecules, sometimes we need to say what those shapes are. And with that in mind, I guess we could look at cyclohexane as an example. Just for fun. So cyclohexane is C6H12. It does kind of look like a weird snowflake. So we can draw that on a flat surface looking like that, but it's not actually a flat molecule. Each one of these carbons is tetrahedral, like the oxygen over here. So in 3-dimensional shape, it actually kind of looks a little bit like a lazy boy. Sounds like a weird comparison. See if I can. So each one of these carbons winds up being that tetrahedral shape. And it works a little bit better with these wedges if I shade it in. So this is one corner of the hexagon. That's another carbon, that's another carbon, that's another carbon. And so he kind of looks like a little bit like, I guess maybe a lazy boy is not the best example. Like a lawn chair that reclines a little bit. There's your headrest, there's your footrest, these are your armrests. So, and then when you take that, it actually can change shapes a little bit. It winds up trying to show that three-dimensional shape in 2D. You kind of have to use some forced perspective, and chemists may come as a surprise to you. Chemists are not known for their artistic abilities, which I think is unfair, because I think this is actually a really elegant way to show that in a way that everybody, regardless of your ability to draw, can show three dimensions. So we'll keep practicing with this, and again, and it goes on from there, because then we start looking at how does this hydrogen interact with, if we had, say, another carbon on this side, that hydrogen, that carbon facing the same direction bump into each other, and that causes some really interesting interactions. Basically, when you get to organic chemistry, we start looking at things in 3 dimensions in a way that we're just going to scratch the surface of in this class. It takes some getting used to, but it actually is pretty fun. And I will use this as a pitch. You should play more video games if you're going to take organic chemistry. There's actually been a strong correlation shown between your ability to visualize organic molecules in 3 dimensions and the amount of time that you spend playing video games, because 3D video games force you to look at a 2-dimensional surface and for your brain to fill in the gaps of what things look like in 3 dimensions. Right? You're used to looking at a 2D surface and seeing 3 dimensions and rotating things around, imagining what it looks like. So they've actually done some peer-reviewed journal articles saying that students who do better in organic chemistry also tend to play more video games. Of course, there's some lurking variables in there. Who's taking stats? Anybody in here? What's a lurking variable? Something you didn't take into account. So it's correlated, it's not necessarily causative, because it could just be that white men with lots of money play more video games than other demographic groups. And organic chemistry is designed in a way that allows white men with lots of money to do better on organic chemistry. So it could be that there's other variables in there. It's not something as simple as if you play video games, you'll do better in organic chemistry. But I kind of like to think that it is. You just have to be aware of those lurking variables, though, right? All right. So we already mentioned double bonds a little bit. How do we get double bonds? We're using our same procedure. What happens to give us double bonds? Yeah, let's look at I guess the example that's on this page is carbon dioxide. We're going to do the Lewis-Dot structure for carbon dioxide. What do we start with? What goes in the middle? Carbon has more vacancies, right? So carbon's going to need to share more, which means it goes in the middle. You put your oxygens on either side. How many electrons do we have to work with carbon or with carbon dioxide? You have 4 from the carbon and then 2 times 6. So 4 electrons from the carbon, 2 times 6 electrons from the oxygen, 16 electrons. I keep writing total, but remember that's total valence electrons. We're not including the core electrons because they don't do anything. Only valence electrons affect chemistry. So we have 16 electrons. Where should we start assigning them? Well, we know that we have to have a bond there, right? So we just use 4 electrons. 12 electrons left. So here's where you have a little bit of freedom to decide how to do it. What seems to make the most sense to me is to start at the outside and work your way in. Right, so how many, the way it's drawn here, how many electrons does each oxygen still need to gain? It's got 2. So it needs another 6 electrons. And both of our oxygens drawn are identical, right? So they each need 6 electrons. What's that going to do to our number of electrons that we have to work with? We're going to use them all up, right? So we used all of our electrons. Criteria 1's fulfilled. Are we good? Why not? Carbon needs what? 4 more valence electrons. It's only got 4 electrons. It needs 4 more. We don't have 4 more to give. So this is when we start using double bonds. When we run out of electrons, but we still haven't filled all the valences yet. And the way we do this, we already ran out of electrons, so we're not just going to throw more electrons in there. We can't do that because that's making electrons out of nothing. Now it's not neutral either. So we erase a pair of electrons from one of the carbons and turn it into another bond. Now is it stable? We're closer, we're better, right? We need to erase another pair of electrons and attach it to the carbon. Which one should we do? Out of symmetry, we would normally think, we inherently as humans think of symmetry as being more balanced, because usually that's accurate, and also just because of the way our brains work, we like symmetry. Seems like it would make more sense rather than doing a triple bond on one side and a single bond on the other. And we're right for the most part. And so we only wind up seeing double bonds when we run out of electrons before we fill the valence. Right? So keeping this running total going and remembering when you get to 0 becomes a really important part of this. All right, as far as shapes go, how many things are taking up space around this carbon in the middle? Yeah, it's got a total of 8 electrons, 4 pairs of electrons, but there's only really 2 things around the carbon, right? There's 4 electrons between carbon and this oxygen, 4 electrons between carbon and the right-hand oxygen. If only 2 things are taking up space around that central atom, how far apart could they get in terms of an angle? Furthest apart you could get would be 180, right? So when we say how many things are taking up space, we call that how many electron domains. A domain is just an area, right? So this carbon has 2 electron domains around it. 2 things taking up space. Which means the furthest apart they can get is 180 degrees. What does that look like in terms of 3 dimensions or 2 dimensions? Or technically 1 dimension. Yeah, we call this geometry, this molecular geometry, we call it linear. And that is actually what we see. We actually look at these shapes. We actually see a carbon and oxygen on either side, and it's totally linear. Those 3 nuclei are in a straight line. All right, so we talked about this a little bit when we first brought in the idea of covalent bonds and non-metals. So we've actually done the Lewis dot structure for these first 3 already. Well, let's practice it. Let's start with chlorine. 2 chlorines. How many valence electrons does each chlorine have? Yeah, 7. Start, count over columns, skip the D block. So 2 times 7 electrons, 14 electrons to work with. We can start by doing that, right? 12 electrons left. How many does each chlorine still need? 6. That's convenient, right? No electrons left. Everything has full valence. What about oxygen? Each one has 6 electrons, which means we have a total of 12 electrons to work with, right? So 10 electrons left. Now we can't just fill up the outside, right? So fill up one side. I only like dealing with these electrons in pairs. Like we talked about earlier with the free radicals, unpaired electrons are super unstable. So even though we're going to run out of electrons before we can fill everything's valence, I still like to only keep it in pairs. Because now what do we have? We have one oxygen that's stable and one that's not. So what do we have to do? Bingo. Right, so chlorine versus oxygen versus nitrogen, they all have different properties. They're all gases at room temperature, but we wouldn't want to try breathing chlorine, right? Chlorine is really, really reactive because it's got these 2 nonmetals that are both, but only with a single bond between them. Oxygen is still reactive, but it's less reactive than chlorine. What about nitrogen? What is nitrogen going to look like? We count up our electrons, we're going to wind up with a triple bond. Do we want to breathe nitrogen? Not pure nitrogen. 80% of the atmosphere is nitrogen, so it's not a problem as long as we have enough oxygen to go with it. The problem is that nitrogen is too unreactive, it's too stable. Our body can't breathe pure nitrogen. There have been some headlines about that recently, a more political issue. Anybody think of them? Several states that still enforce the death penalty have been using nitrogen asphyxiation as a means of carrying out the death penalty. Basically, you just gradually replace all of the oxygen in the atmosphere with nitrogen, and then there's nothing for them to breathe. So breathing pure nitrogen is not going to work either.
I feel like you would just kind of go to sleep.
That's the debate. Is in theory, if you do a good job of filtering out the CO2 as you're introducing more nitrogen, then yes, it should just cause nitrogen narcosis and then you lose consciousness and never wake up. However, the way that these states are carrying it out is just by using a mask on their face with nitrogen, and they're not filtering out the CO2. And CO2 levels rising in your bloodstream triggers panic response and causes a lot of pain. So it could be done humanely, but it's not being done humanely. I think Louisiana is set to carry one of those out this week. They banned nitrogen asphyxiation as a means of killing animals, of euthanizing animals because it's inhumane, but they're going to go ahead and use it on a human because the cell.
Do you have a quad bond?
Between certain metals, you can make a quad bond. It's not very stable and doesn't last very long. It's really just sort of as a novelty. Basically, what winds up happening is you don't have enough space in 3 dimensions to put 4 pairs of electrons without them overlapping with each other. You can do a triple bond pretty easily. You can't do a quadruple bond. All right. That's a good enough place to stop for now. We'll start with Lewis dot structures for polyatomics on Wednesday. Oh, I have everybody's quizzes too, your functional elements quiz. Do you want to come up and grab that? Otherwise, I'll hand them out on Wednesday.